Oh shit. So right now, I just big chillin'. Okay. Let's make sure we good. What up? Definitely didn't, but that's some shit that I can make on my own. I'm just gonna be honest. You're crazy for actually saying some shit. Cause nah, I'm just gonna say this. That was not worth any fucking. That was not worth anything. And it's not like I'm even using it, so it doesn't even fucking matter. Alright. I wanna watch this again. This shit was cool. Alright, so right now I'm just fucking.
Okay, so next we're just
in
going to
the
look
process
at
of studying.
gaining access to something from the ground using a pull through.
Got some pretty
Okay,
big tests coming
loads
up.
of ways of getting ropes over. You can use little weighted bean bags. You can chuck them over. You can use catapults. You can use fishing lines. Obviously, there are dangers involved with chucking little bags of sand around. Somewhere offshore, lots of pressure gauges, something like that. Not ideal. Or you can just use the old tree surgeon's trick, which is we create a couple of coils in your hands with your rope, and then I'm going to make like a little coil and choke it through. Okay, so that is our throwing weight, if you like, and then I'll take some more coils in my hands.
He just gave me a new way of how I'm gonna do this next time I fucking gotta throw a
I
rope.
need both sides of the coil, and then I can throw it over the beam, in theory.
Beautiful.
And it comes back down again. So once I've got my rope over the beam, I'm just going to pull a bit of rope onto the floor and then tie 2 alpines next to each other. And then I'm going to tie the middle of the rope in here. So I'm going to tie a barrel knot between the 2 alpines. Tie what you want really, but tie a barrel knot. Pull it tight, and then what I'm going to do is, you think that you want to pull that up, but you don't.
No.
You want to hoist the alpines. So that's what you have going up, 2 alpines. You want both the alpines coming over the same side of the beam. All right, so try and keep my ropes from twisting as it comes over. So if we just split these now, see what's going on.
So what he's doing is he's making
So if I now get 2 carabiners and fasten them into there,
a 100% safe pull-through system, I'm pretty sure. So
pull
that
those up, and that is you kind of
you
standard
can attach
pull-through,
yourself
but
and go up
when it is over,
and take
the
yourself
great
off the
thing
beam.
with this is we've only got 3 ropes down here now, so it's impossible to have 100% failure. So even if you were
listen.
complete numpty and you got on the wrong side, you would still have a backup to protect you. All right? So if we just attach these 2 carabiners to these 2 ropes, that's your bog standard pull through. But if we're accessing from the floor, we have
He's
no
gonna do
idea
some cool shit here.
how sharp or how hot that edge may be. Okay? So there is a way of doing it so we eliminate any sharp edges or any potential rope meltages. What we do is we get 2 wire strops.
This is the cool part, yeah.
And then I'm going to pull them up a bit so I can see what's going on. So 2 wire strops. And then what I'm going to do is we'll attach a pulley to each of these. And then put the pulley around the rope.
So what he's about to do is get those while staying on the ground. He's going to be able to get those wire ropes up and around that beam, up above. And what's going to happen while he's on the ground, those cables there, those
just get them underneath everything.
those are going to take the whole weight load off the rope.
They're not getting twisted before you set off. Make sure that you've not got them on the tag line or anything like that. So I'll hold them up now. Make sure all your gates are done up. So when the alpines go over the beam,
Ready? Watch this shit.
they now rest against the pulleys. So all
Boom.
the weight is on the strops.
Yep.
And none is on the rope.
Crazy. Crazy.
Okay, so anytime you ground rig, you got your 10-foot piece of steel that goes around the beam.
For me, it's a 5-footer most of the time.
The setup is shackle goes on the opposite side of the pin. This is going to go around the beam and it's going to attach to this. So your rope goes right here.
What that is called the master shackle.
You go around.
Its quality's not great, but
It's going to attach to this.
look right here. So the thing in his hand, that's a loose shackle, okay? Well, that's called as a free shackle, all right? This is rock and roll style. This is what is normal throughout the industry because it's easier and it's safer. So right here on my mouse, that is the master shackle. The master shackle is what is taking the load. This is what's actually holding everything together. This is what's holding this leg that goes down and this leg that goes around the beam, like he is saying. And so this 10-footer is connected to the master shackle and it's loose, okay? It's connected here and then it's free here. So once it gets up to the top, when I'm up there, what I'm doing is I pull this thing up, okay, by rope. It gets to me, I break the rope over the beam with my foot, okay? Now my foot's holding everything. Plus physics, breaking it over a 90-degree angle takes the weight, blah, 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 whatever. Either way, you're holding the weight with your foot. You then throw this 10-footer around. For me, it's a 5. But in this instance, you throw this 10-footer around. And over here, you see this thimble? That's what's at the end of this, okay? Is this thimble. Just like right here on the other end. And it comes back into the free shackle. Okay, that's it. And then it's done. You put your burlap bag around, and boom.
This. So your rope goes.
Your rope goes
right
in
here.
the master shackle. Your rope goes in the master.
You do the bowl line.
Yo. Okay.
And that's ready to go out.
Yeah. Okay, we're good.
You can see. This goes around the beam and attached to this. Keep this area clear of all of the gap. Rope, pin, all the time. Free shackle.
Rope. So it goes pin,
So that
rope,
the rigger up there
steel, shackle.
is free to open this up and attach this.
It makes everything easier when things are clean to work with. And safer.
Hey, I'm Josh with Columbia Safety and Supply, and in this video we're going to show you a few gear options designed specifically for stage rigging. Unlike typical at-height industries that have highly colorful equipment that often indicate a specific purpose, the stage rigging industry is unique in its need for all black equipment. This includes rigging, hardware, ropes, and even fall protection harnesses, all with the goal of not being seen or drawing attention away from the performance. Luckily, we've curated a category specifically for that industry that contains all the rigging equipment you might need in an all-black.
See this.
There's Daniel ascending a rope after fixing his rope. So Daniel, how fun was that?
That's pretty fun.
I bet.
Just,
Sure.
the rope kept sticking to the chain, so
Yeah.
fixed, that's all.
Yeah, awesome, man. Good job. Moving on.
This video is going to show
Right there, that guy had to fucking go fix his rope. He got it all tangled up and shit, it seemed like. And, yeah.
how to tie a bowline in a situation where you got a rope coming down from the beams, and in this orientation.
Now, do you want me to, let me swing to you? Or we can drop them together?
Well, if you want to drop them together, we can just drop them.
So,
So this is what I do. This is my job. What they're doing right now is the type of shit that I do. It looks like they're about 60 or 80 feet up. Right now he's sitting down on the beam, getting his rope ready. He's clipped in to the steel. What he's gonna do is he's gonna pull it up, and he's probably gonna step onto his rope or into the bowline. Yep. He just put his foot into the knot. And now he's about to disconnect the 5-foot steel from the free shackle just now. Take the pin out. Now you put the pin back in. Now he's going to take his 5-footer. He's going to pull it over the beam. He's going to put his bag in the 5-footer. He's then going to take his rope and let it in slowly. Once his partner is ready, they will send it together. See, he's putting his bag in the 5-footer. That ain't going anywhere. It's connected to the master. Don't freak out.
Downstage right, 1 ton coming in.
See, so you signal to your ground rigger to let them know, hey, shit's coming in, boys. But yeah.
Decided it wasn't gonna do any good to get mad, so I wrote a song about him instead.
Oh boy.
It goes like this. Were you born an asshole, or did you work at it your whole life? Either way, it worked out fine, 'cause you're an asshole tonight. Yes, you're an A-S-S-H-O-L-E, and don't
Holy
you try
shit.
to blame it on me. You deserve all
That's
the
fucked.
credit.
That's
You're
fucked.
an asshole tonight.
That's fucked.
You were an asshole yesterday. You're an asshole tonight. And I've got
That's fucked up. Holy shit.
I'm Johnny from SXS, part of the production team for the What Now Tour. The guys are just setting up here now at the Barclaycard Arena in Birmingham. This video is about arena rigging, and in this I want to talk through a few basic principles of what we do when we're working in arenas and the workflow and the process and the safety management. Arenas in the UK vary. Some have a mother grid whereby the main roof structure gets dropped down to the floor, at which point we attach our chains to it. Other times, like this venue here, cherry pick it, drop down to the floor, at which point we attach our chains to it.
So when he says drops down to the floor, the roof comes in. Yes. He's not even joking. Yes. This is all like connected to the actual roof, and it's connected to motors, chain hoists. Sorry, this thing right here. See how it's got that? Sometimes they have a mother grid, and there's a device somewhere on the ground. You can just click and it all comes in.
Other times, like this venue here, cherry pickers have to get the riggers up into the roof and we attach our chains
Cherry picker, boom lift, same thing.
into the roof. In both instances, the reason for that is that the chain can drop down to a motor and then the motor can lift the truss up into the air. So what you see behind me here is a series of trusses. Some have lighting on them, some have video, some have projection screens, some have projectors. In addition to that, we've also got some line array PA systems which are also flown from overhead as well. All of the items that are lifted into the air either have to have some kind of redundant safety line on them or they need to be double braked. What that means is that if the motor were to ever fail, the equipment wouldn't fall, it would be held in place either by a secondary braking system or a second steel line which will hold the equipment should the motor ever fail. So the first thing we do when we get to arena is we mark up a floor. What that means is we're transposing the information of where all the rigging is going from our 3D visualization into the venue. That means that the rigger can then attach the motors overhead in a position where the truss needs to end up. We want to avoid working at height as much as possible. So on this particular production, only 2 or 3 people have actually been up in the air. Everything else is done at ground level. All the lighting, all the video is rigged onto those trusses. It's set up, it's programmed, and it's addressed, and then the whole lot lifts up into the air in one go. That way everyone works at ground level, which is much quicker, safer, and more efficient.
So this is like, I know like this stuff. We gotta find some like, oh, 2 tons, babe. 2 ton, babe.
Hello, everyone. My name is Glenn Gordon, and in the entertainment rigging industry, they call me Gigi. Well, in this business that I'm in, this is the type of business that you can travel the world and doing this type of work. I've been very fortunate because I'm based here in Atlanta, Georgia, but I've been very fortunate because some of the local labor companies here that do this type of work, there's several different parts in this type of business that we're in. You have the entertainment rigging portion of it, and you also have the stagehand portion of it. Well, to become a ground rigger, this is a very serious task, and I was fortunate because a friend of mine named Andy Hansel gave me an opportunity to show what I can do in this type of business. And of course, he looked at the fact that I was ex-military. And speaking of ex-military, I did 15 and a half years in the military, and I was a drill sergeant. I also was a crane instructor, and I taught rough terrain forklift as well as the 25-ton hydraulic roll crane down at Fort Leavenworth, Missouri, of course. But Andy House, listen, and that's the key thing. Listen, that's the key thing. How to become a ground rigger. This is what we go through, and we kind of like point out exactly as to what is what. 5 baskets, leg, stangle.
No.
I don't know, in my perspective, if you're in the right industry. You have to work safe 100% at all times. Safety starts with the attitude of the individual.
Alright, let's see.
Safety starts with the attitude of the individual. It is in you, and you just do your job safely. And if you have to think about it, then is it safe what I do? Is it not safe? Then I don't know, in my perspective, if you're in the right industry. You have to work safe 100% at all times. First of all, riggers hang things, all kinds of things. When you go to a concert, you walk into a concert hall, and all the lighting, audio hangs in the air. And somehow it has to get there. And obviously all the stuff needs to be set up on the ground. And we are the guys that climb around in the ceiling and hook up all these lighting and audio, what is set up on the ground, so it can get flown out and eventually lives on top of the stage. So live events and light shows and audio and video, laser shows, all this kind of stuff can happen, and that people can enjoy their time safely. My aunt had a circus in Berlin. It started off as a circus, as everybody knows, and turned into a cultural circus. And when I was 10 years old, I started climbing my first truss and realized that I wanted to work for her. I grew up initially in Munich, Germany. I moved with 16 by myself to Berlin and went to school for 3 years for entertainment, live entertainment. And that's how I got into this industry. And this is now 12 years ago. Safety is obviously one of the biggest parts, because we have people coming to events. They are walking under our stuff we are hanging.
Yeah. Maybe this probably won't teach me much, but let's see how informative it is at least. After this, I'm gonna do another search, try and find some like more complex videos.
We're going to talk now about pulley systems as they're used for mechanical advantages, and specifically we're going to address these 5 simple rules for a simple mechanical advantage. This is stuff that's been handed down over centuries through the mariners industry, and they still hold true for today in understanding these pulley systems. The first rule is, if the rope is tied off at the anchor, it's always going to be even. It's going to be a 2-to-1, a 4-to-1, a 6-to-1, 8-to-1. Always going to be even. Here we have a 2-to-1. It's tied off at the anchor. Rule number 2 says, if it's tied up at the load, it's always going to be odd. It's going to be a 3 to 1, a 5 to 1, 7 to 1. In this case, we have a 3 to 1. If I were to pull from right here, it would be a 3 to 1. Rule number 3 addresses this pulley right here. Rule number 3 states that the last pulley at the anchor where the rope goes to the haul team is a change of direction. And it really doesn't offer us any mechanical advantage. It's simply a convenience as a change of direction, okay? Another way to think about this, any leg of rope that goes from an anchor, myself as a haul team in this scenario, I'm part of the anchoring system. So any leg of rope going from an anchor to an anchor offers no mechanical advantage. It's only these legs of rope that go from anchor to load that give us the lift and the mechanical advantage. Change of direction, rule number 3. Let's look back here again. Rule number 1, if it's at the anchor, it's always going to be even. Rule number 2, if it's at the load, it's always going to be odd. Rule number 3, the last pulley at the anchor is a change of direction. Okay? Rule number 4, and we can stay right here. Rule number 4 states that you can count the number of pulleys, add 1, and that's going to tell you what the mechanical advantage is. So let's pretend we don't have this CD here, and I'm just going to haul from right here. And we have this 3 to 1, a Z-rig. I have 1, 2. I add 1, and it says I have a 3 to 1. Another way to look at this is I have 3 legs of rope going from the anchor system to the load where this pressic is. 1, 2, 3. I'm pulling on 1, and I have 3 working for me, hence the 3 to 1. Okay?
This makes
Our
it a
last
third.
Rule number
just so
5 states a simple pulling on the haul of another simple mechanical advantage becomes compounded, and you multiply those two. So what do we have here? We have this blue rope that's an obvious 2 to 1, and it's pulling on the end of what we have rigged here is a 5 to 1. How do I know it's a 5 to 1? Well, let's go by our other rules. It's tied off at the load, so I know it's going to be odd. I have how many pulleys? Well, I have a double shiv right here, so there's 1, 2, and I have another double shiv up here, 3, 4. I have 4 pulleys. Add 1, that says it's a...
I missed him talking about this next part.
To the load, where this pressic is. 1, 2, 3. I'm pulling on 1, and I have 3 working for me, hence the 3 to 1. Okay? Our last rule, rule number 5, states a simple pulling on the haul of another simple mechanical advantage becomes compounded, and you multiply those two. So what do we have here? We have this blue rope that's an obvious 2 to 1, and it's pulling on the end of what we have rigged here is a 5 to 1. How do I know it's a 5 to 1? Well, let's go by our other rules. It's tied off at the load, so I know it's going to be odd. I have how many pulleys? Well, I have a double shiv right here, so there's 1, 2, and I have another double shiv up here, 3, 4. I have 4 pulleys. Add 1, that says it's a 5 to 1, okay? I can also count the legs of rope between the anchor and the load, and I have 1, 2, 3, 4, 5. So all my other rules are incorporated right here as well. This is a 5 to 1 if I were to pull from right here. But say this is just not giving me enough power, and I'm really getting wasted. I need more horsepower on this thing. So I can quickly add a 2 to 1, represented by the rope here. So I have the 2 to 1 multiplied times the 5 to 1. This is a compound 10 to 1.
Wow, okay.
What's the trade-off? Nothing in life is for free, is it? The trade-off is I have to pull 10 feet of rope here to move that load 1 foot.
Yeah.
But it's relatively 10 times easier, discounting any of the friction and stuff within these pulleys themselves.
When he's saying 10 to 1, 5 to 1, 4 to 1, 3 to 1, that's just indicating that it's 3 times lighter, 4 times lighter, 10 times lighter. But then that means you have to pull more rope, like he just said right there.
Hey everybody, Brian Blackmore with Church Production Magazine.
Because what it's doing is you have to take more rope to get more length because you're able to get more pull out of the less rope because it's able to take more weight load. This will be fun.
Okay, so next on the list, we're going to have a look at a counterbalance off a chest ascender, and then we're going to take the casualty down through a re-belay. There's a couple of ways you could access him. You could access him from below, or you could access him from above. It purely depends on the situation at work, really. Okay, so first thing I'm going to do is I'm going to take his backup line. Try not to pull through too much slack, because I'm going to transfer onto it. Just make sure that ASAP's not dropped too low. Just transfer onto that. Try not to straddle your casualty too soon. You want to be with him, but not straddling him, just so you can keep everything clean. All right, I'm now going to change into descent. And then I'm just going to transfer my backup over. So it's important with this that everything's clean and you know where these loops are going all the time, all right? So I'm just going to put that in there. And just take our hand descend up. Try not to stand on our casualty. Knock that off. Okay, I'm now going to abseil down level with his chest point, all right? Make sure it's nice and neat all the time. I want to get to about here. And then I'm going to use a chain of crabs, one into his chest. So it's really important when you join the carabiners together that you know where your loops are. See these two loops here, the one that's coming off him and the one that's coming out of our descender. We want our hard link below it, because if it's not below it and it's in here, we have all kinds of trouble when it comes to the re-belay. Really important. You make your connections and then you know where your loops are going, all right? So that's in there. I now need a backup from him to me. So I'm going to use his long cow's tail into my central D-ring. Do the gate up, all right? So I've got 2 points to him, I've got 2 points. I can now take his backup off. And depending on where we're going next, I might need that. So I might just steal it. And then I'm going to take his descender as well, because I'm going to need that. Okay, so next, we've got our 2 points to him. We're sure that the loop's clear. We need to lift his weight off the chest ascender, so we're going to use his fall arrest attachment point there. If it's an old crawl, there will be a small carabiner hole there which you can lift him off. And we're going to use his hand ascender because it's the nearest thing to hand. I'm just going to remove his foot loop out of it. I'm going to put a carabiner in. I'm going to put the carabiner in the top, just so it gives me an extra bit of height. I'm going to put that one in there. Sewn termination where my foot's going to be, all right, so that's going into there, and then spin that, clip that in. Nice and neat and parallel, nice and clean, all right. The neater it is, the easier it is. And then I'm going to look at it, I'm going to need a couple of inches, so just slide it up a bit higher if I can. And then, foot in,
Yeah, step in, he's gonna lift his buddy up.
And then I stand up straight. This is not difficult. I'm not lifting with my leg, I just lift with my arm. An inch.
See?
Another inch.
Now his friend is disconnected
nice
completely.
Wasn't traumatic. Sit down.
And connected
and then
to
I'm
him.
just going to pinch the sling, pinch both sides, kick my foot out.
I'm pretty
and then
sure.
I'm going to lower his weight onto this chain of carabiners. Pull that out.
Yeah, now his buddy's connected to him. This is like if you had to save somebody. That's 5 minutes.
I snatched him. See where we're going. I'm just going to have a quick turn him round. Just get it so you can see it. But the loops are clear. At this point here, you want to check that the loops are clear. Because if they are between this hard link, again, you know, at this stage we can sort it out. If you get a bit lower, you can't again. All right, so nice and simple. Friction carabiner on. 2 persons weight, so we need a friction carabiner. Check the ASAP's running. And then nice and steady down. It's not very far this, but down till you're just below where you're attached with the re-belay. And then we're going to transfer from one descender to another. So I cunningly stole it earlier, so I didn't have to go foraging around in here. We're going to put this descender so that Chris is hanging off both the descender and my D-ring, all right? This is quite important, so it goes through that carabiner and there, do the gate up. Now as we transfer, this all stays clean. I'll show you. Just take my friction beaner out. Again, checking my loops, pull myself over. New rope in, and then I'm just going to pull myself over. Again, it's not difficult. So that I'm keeping all the height, I'm not losing any height. Lock that off. So if I just were to abseil just a little bit on this, these two are under equal tension, all right? If they were any bigger than this, you wouldn't want to do it like this. You'd want an extra point on. But I'm happy that those two are in tension, so I'm just going to take my backup off. And I'm going to put it on the other rope that we're descending down on. Put it on, and I'm checking everything's clean. Once again, I'll just lift my loops out of the way. I mean, you can chuck these over a beam or whatever, just to make sure it's all free. It's nice and controlled. Nice and easy. Close that one up. Again, double check it's clear. And then friction beaner on again. I'm ready to go down.
And in 8.5 minutes, he saved his friend. It's pretty good. I like these guys.
Okay, so we're just going to have a look next at a casualty who's fallen onto a set of fall arrest lanyards. We've got to get him down. There's 2 ways we can do this. One is like an A-climb rescue where we lower them. So I've got a pre-rigged ID and a pre-rigged ASAP lowering system. I'm just going to climb up to him, snatch him onto these and lower him off. So all I need to do first is take my sling, pick somewhere structural, shove it up through there. And feed a bit of slack in. I'm going to clip that into his chest. Always better to pick him up from the point which is attached, so that's going in there. So that'll be one point, lock that off. I'll give him a backup as well as it's Irata.
He's referring to Irata, it's the
Feed that out, clip that into his chest as well. And again, with all these things, there's a few different ways of doing it. I could put a 3-to-1 in, or I could try this. We'll just get just going to get my hand ascender and stick it on the downside of his rope. Just going to stick my foot in, which is effectively my counterbalance, unlock it, and hopefully, if I just weight it and pull him up, lock it off again. I only needed an inch to unclip those. Take my jammer off.
Yep, now he doesn't need that because he lifted him. That's for friction. See that carabiner?
Put my friction beaner in.
Yep.
Make sure he hasn't got any other connections and that he's going to be clear from the structure. And then I can just lower him down and everything should just run. Just got to be careful when you're lowering someone down something like this that they don't snag on anything.
Yep.
So option number 2 with a rescue from fall arrest is actually snatching him onto me and taking him down. When you've got like a lattice structure like this, lowering a casualty down it who's completely immobile might be a bad idea. You know, get snagged in it, get hung up on it. It wouldn't take much for it to become a problem. So I'm going to rig some ropes and I'm going to go down with him. So I've got pre-rig 9s again. Just clip them in as high as I can.
And then he's just gonna do what he did with his friend.
My name is Tyler.
And I'm John.
And together.
Shut up, John.
Hello, all.
Shut up, Tyler. What are you doing? No, 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 no. No, 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 no. What are you doing? What the fuck is this guy doing?
Moving. Hold that. Damn jetpack. Fuckers. What in the hell? Thing is stuck. I'm gonna set my termination. Huh? Yeah, I got this. I got a 9 right here. Yep. No, I brought an extra.
Yep.
All right. Moving on. Now these lines go on this side of the beam, right? Moving. Okay. Gotcha. Moving.
Is there no safety lines in this building? I'm like pretty sure this guy is not clipped in. I mean, I don't care, but
Moving. Hold tight right there. Lock it off. Talk to me, man.
okay, I think he's safety it off through his rope.
Come on, you little bitch. Moving.
He's the one installing the full protection. This guy's probably one of the safest guys out there.
Moving. Hold that, lock it off.
Hi, it's Eric again, this time in a beautiful hop field. In this video I'm going to be talking about the kind of slings we use in our industry. And yes, we are still talking about events rigging. Steel wire rope, polyester round sling, steel wire round slings, flat webbing slings, and chain slings. Steel wire rope slings with a pressed eye termination are amongst the commonest rigging accessories that we use. They are reasonably fireproof, but the aluminium ferrules used to form the eyes will be weakened if they're exposed to heat, especially from the latest generation of high power lighting fittings. If used as a basket arrangement around a beam, they must be protected from sharp edges by a good thickness of burlap to make the turn gentle at the beam edge. If choked, it is important that the first bend in the wire rope is not too close, not within 2 centimeters or so from the ferrule, as this creates a weak point. If used to sling flown aluminium structures, the hard steel of the sling can easily damage the soft aluminium of the truss. Many people use a clear plastic sleeve to protect against this, but this practice is forbidden in certain countries because of the increased risk of trapped moisture causing corrosion and increased difficulty of inspection. These plastic sheaths are not good enough protection against a sharp beam edge. They are similarly common items and have some advantages over steel wire rope. They can make a tighter turn with less reduction in strength and create a much softer, reduced pressure point in contact with aluminium. They are, however, very much less resistant to heat and so should be avoided where this is a factor, particularly nearer to pyrotechnic effects. The outer sheath protects the inner load-bearing yarns from abrasive damage, tight bends, and particularly to exposure from UV light, so that any damage making the inner core visible must lead to removal from service. In recent years, more and more productions have moved away from using polyester round slings in favour of steel cord round slings. Here, the outer sheath.
1. In the context of ETCP, which approach best aligns with adult learning principles when introducing a new technical concept? A. Presenting lengthy theoretical lectures without context.
What the
B. Using problem-based scenarios relevant to learners' job roles. C. Delivering memorization-based drills with no application. D. Providing minimal explanation and expecting independent research. 2. When designing an ETCP module, which
The rigging triangle is a key consideration when making connections to loads and load hooks. The rigging triangle is formed anytime two or more slings are connected to a load and load hook. Whether the slings are chain, wire rope, or synthetic, the best practices are based on the same principles. Focusing on the horizontal sling angles formed in the rigging triangle highlights several best practices that are very valuable to the rigger. It is important to remember that as the rigging triangle becomes flatter, the horizontal sling angles become smaller. As the horizontal sling angles become smaller, even though the lifting load remains the same, the crushing loads increase. The sling tension is the result of both lifting and crushing. This means as the sling angle becomes smaller, the sling tension and the load at the load connections increase, and the crushing forces pulling the slings toward the center of gravity also increase. The result is that at 60 degrees horizontal sling angle, the sling tension is multiplied by 1.15. At 45 degrees, the tension is multiplied by 1.41. And at 30 degrees horizontal sling angle, the tension is multiplied by 2. These facts lead us to recognize the best practice for selecting proper sling angles. For multiple leg bridles, whether the connection is directly to the load with hardware or choker and basket hitches, a horizontal sling angle of 60 degrees is the angle of choice. This is because the multiplier is only 1.15, the side or angular load on the load connections is limited, and the crushing load is minimal. A tool to use to verify that the slings are rigged to 60 degrees is to remember that a 60-degree sling angle is formed when an equilateral triangle is created. This means that the sling length will be equal to the distance between pick points. It is also useful to remember that increasing the sling length will increase the horizontal sling angle and improve the rigging situation. It must be noted that 60 degrees horizontal sling angle is the best choice, but is also the minimum angle for single wrap chokers and single wrap baskets. There are circumstances where a 60-degree horizontal sling angle is not possible. When this occurs, there are guidelines for the minimum sling angles that can be used with extreme care. 45 degrees is an acceptable horizontal sling angle only for bridles connected hardware to hardware and for double wrap choker hitches and double wrap basket hitches. At 45 degrees, the sling multiplier increases to 1.41 times. The crushing forces pull the slings toward the load center, and the angular or side loading is very significant. 30 degrees is never a desirable angle. However, 30 degrees horizontal sling angle can be used with extreme care when connecting hardware to hardware. Never use choker or basket hitches at this minimal angle. Remember, best practice calls for a horizontal sling angle of 60 degrees or larger.
Calculating load limits with the S279 machinery eye bolt is straightforward. Using two slings in a true inline load, each side will see half the total weight. From the Crosby lifting guide, notice that for a 90-degree horizontal sling angle, the load angle factor is 1. In this example, the total load is 5,000 pounds, which is divided by 2 for each sling leg, and then multiplying by the load factor, which is 1. The result is that each side lifts 2,500 pounds. To select the proper bolt, refer to the Crosby lifting guide. Note that the panel does not mention the S279 because the information is the same for all Crosby shoulder eye bolts. We need to select an eye bolt whose working load limit exceeds the required load of 2,500 pounds, which in this case is a 1/2 inch machinery eye bolt with an inline working load limit of 2,600 pounds. Let's now look at how increasing the horizontal angle affects the size fitting required. For 60 degrees, the load angle factor is 1.155. Again, we divide the load of 5,000 pounds by 2 and then multiply by the load factor to determine the load each sling leg will see. In this case, each sling is loaded to 2,887.5 pounds. We will round the calculated load to 2,888 pounds. Referring to the lifting guide, you will notice 4 columns showing the rated capacity of Crosby shoulder eye bolts at various horizontal angles. Crosby shoulder eye bolts have a catalog rating based on inline loading. As side loading occurs on the eye bolts, they must be down-rated. The smaller the horizontal angle, the greater the reduction in the working load limit. As an example, let's look at the 1/4 inch size. At 90 degrees or inline, the rating is 650 pounds. As the horizontal angle changes, so does the resulting working load limit of the eye bolt. At 60 degrees, the rating is 420 pounds. At 45 degrees, the rating is 195 pounds. And at horizontal angles less than 45 degrees, the working load limit has been reduced to 160 pounds.
See, this is the type of video I want to see.
Didn't have the shaded section underneath, but he put the line in there. And I looked around the room and I saw a lot of people understood it.
Yeah, I'm gonna watch this guy, but I think the audio is only in the left ear, which is weird.
Hi, I'm Rob Stringer from High Point Access and Rescue. The purpose of this video is to illustrate a rope access backup system that we use. There's a document that we've published that describes going away from cow-style type lanyards, so as backups, and going towards a system similar to this. Okay, so the primary part of our system is an energy absorber. So we connect an energy absorber directly into the sternal attachment point of the harness. On that energy absorber at the far end or distal end is a connection point that we use for all of our backup connections. So be that to an anchor or a device, they all come into there. Okay, so this particular energy absorber is pretty much what we need. We need a connection here that we can get off. Okay, so anything that's on your harness that is fixed to your harness that can't be removed, it limits its versatility. So we use that connection there to increase versatility. We can take that off and put it in other things. This is a EN355 rated energy absorber, so it meets the standard. The other thing we've added onto there is this connection point. So this is a bolt-on connection point. And it's quite good because we can make 3, 4, even 5 connections in there if you needed to. Usually 2 or 3 is what you operate with. Okay, so we've got our energy absorber there. The primary, well, our preferred device for up and down work for backup is Petzl ASAP. So that Petzl ASAP would connect into the distal connection point of that energy absorber. So the majority of our work, or the majority of work that's straight up and down, that's the system that we'd use. Okay, if we wanted to do a rope transfer, we'd probably use a device similar to this, or this device. So this is an S-Tech duck. S-Tech duck is pretty easy to adopt into your system because it's the same or very similar to a Petzl shunt. We connect that into our system, straight into that distal connection point of the energy absorber. Back into there. So we can do a rope transfer from one to the other. It's important that we take this device off the rope, that we don't leave it hanging on there. We don't use that connection point as a stowage point. So we don't leave this sort of thing happening. So anything that's, whenever this energy absorber is in service, we don't stow things on there, so we take that thing off. Now that's a good length for a connection onto this backup device. It's usually always within reach. There are occasions when you want that to be longer, so that's not usually a problem. We can extend the length of that quite easily by choking it. Through there. So that gives us quite a long one. It's not something that you use normally, but there's the odd occasion where you need to make that connection long. And I guess we can make it quite short. So you've got options. So with the 60 centimetre Dyneema, you've got options of anywhere from 1 carabiner length to out to 60 centimetres with 2 carabiners. Another component in our system is a second Dyneema sling with 2 carabiners, so we keep that as an extender. In this case, if we wanted to change over to an anchor, depending on the surface there, we could use that to wrap around the anchor. We connect that directly in to that energy absorber. That means we can drop out that second connection. So with those few components, we have the energy absorber, we have the ASAP, we have two Dyneema slings, 60 centimetre extenders, and we have a second backup device. With that, we've got huge versatility in our backup system. That's primarily what we take. On the odd occasion, we'll include wide opening double action hooks. So if we wanted to make a wide lanyard to climb up a tower or something, we could easily use that. With that choked onto here, we get quite a good length lanyard. Quick summary: energy absorber, distal connection to the energy absorber, that's where all our connections are made. That maintains the energy absorbing capability of that. One thing to keep in mind is at no point should we connect this back onto a harness. Anytime we've got this in service, this energy absorber in service, we should never have a connection back to the harness because that defeats the purpose of that whole energy absorber. Our preferred positioning lanyard now is something like this, so it's an adjustable webbing lanyard. This particular one's a Metolius lanyard. So the Metolius lanyard has a rating on there. It's a climbing lanyard, I believe, but it has a rating, a 300-pound rating, or 136 kilograms. So we can make that quite long, so it can be quite a long lanyard, and you can make it quite short. One of the good parts about this lanyard is the length when it's shortened right up. We need good strength with this, and we need good adjustability, which this has, and we need it to be quite long, and we need it to be very short. So there's quite a bit we ask out of a lanyard. Okay, so that's our primary positioning type lanyard, rather than a cow's tail through a croll or something like, through a chest ascender or something like that. Okay, so that's that one. The second lanyard attachment we have is a cow's tail.
This is what I have.
So it's a sewn dynamic lanyard.
No, I don't have this, but
if you Hi, I'm Rob Stringer from High Point Access and Rescue. In this series of videos we're going to talk about collapse rate. So the first one to kick it off with is a comparison of a few different pulley systems, and we're going to use collapse rate as one of the criteria for evaluation. So we've got our bit of a scenario set up here. So we've got a load that's over an edge, comes up through a high directional, back into a pulley system, which is anchored. So back at the anchor here, we've got a progress capture device. We've got a haul team there, and we've got some sort of rope grab or haul cam along that line. So our criteria. Rate. First one covered application. This one's going to cover simple and compound MA, and the next one will cover complex MA. Okay, so we've got our simple pulley system set up here. Now the definition we use for a simple pulley system is the travelling pulleys are moving in the same direction and same speed as the load. So as we haul this thing up, that should be what we see. So as we haul it up, we see that these
How to calculate the load on 4 lifting points. Step-by-step guide.
I think we gotta do arena.
Hello everyone, how's it going? This is Jeff bringing you a PowerPoint on entertainment rigging. I will be explaining a wide range of things here, and not for only newcomers, but also for veterans, guys that have been doing this for years. There might be a thing or two that I show you here today that might have slipped your arsenal of knowledge. So if we can move on to this next slide, I'll show you what we will cover here. I broke it up into 3 units. The first one being basics, the second one being intermediate, the third one being advanced. During basics, we're going to learn 5 lessons. What is rigging? Types of rigging, rigging venues, structures, and gear. Second unit, we're going to go over stage position, bridles, hanging signs, knots, and lifts. And the third unit, we're going to go over calling bridles. We're going to go over plots. We're going to go over hung, manually operated, or motorized. Lesson 2, we're going to go over 3 different types of station, a capital I. We do walk on top of these and we do hang from these. We hang steel from these and we wrap up signboard picture you see, or 2 pieces of steel together through fabric. It will not be a beam or eye bolt, and then you'll put the gack with a shackle, and then you will, as you can, what we call extension cords. It's called an Edison cable down the line, and then you got to reach an intersection. Steel on the beam, because once the steel or the bridle invest in a hard hat, I personally right. Now, I used to get confused about upstage, downstage. Sometimes I look at the view of an artist and I'm like, that would be upstage, going forward. No, upstage is behind you. And the reason they did that is because back in the Shakespearean days, the stage was actually on an incline, like a ramp. So that's a good way to remember stage left, stage right, upstage, downstage. So moving forward, on the bottom half of this diagram, there's these yellow circles where you have to call a bridle. So this top half of the bridle, the one that actually like hugs the beam, is called a basket. Basket on this side, basket on. Not in the business of being an artist, but this is how you would lay it out before and work with bridles. You want it facing a certain way all 3 days of the show. So this is where these 2 lines come in of the loop. Let me do that one more time. And this is how you undo it. The reason why this knot is so great is because no matter how much weight is on it.
I had to take a picture of this for the boys. Because my brother... probably wouldn't mind.
It's very easy to undo. And then once you twist it again, you can move the whole bridle points. Usually you don't do this anytime in the beginning. It takes a while until you start calling points and chalking the floor. But it's pretty good to know early on, just so you can get your hands on whenever that
good thing I know
come
this.
up. So when I say calling points, as we talk to get 40 foot, let's look at the other side. Just to do a quick upstage truss and a downstage truss. And let's say together, this would basically be standby, but this is try to memorize the magic number, which is 3.28, and centimeters to inches, or inches your metric units. But it's very important to learn because you do get plots from overseas, and you start looking at these numbers and you're just like,
our speaker that weighs right around 40 pounds, it needs to have structure above it that is capable of holding 5 times to 7 times to 10 times more weight than it is capable of. 5 times is the bare minimum. So 40 times 5, that's 200 pounds that it needs to, at a bare minimum, be able to handle. Now, like I said, 7 times or even 10 times is actually what's preferred. So let's go with 10 times. This is a 40-pound speaker. 10x means the structure that we put ahead above needs to be able to handle 400 pounds before anything's gonna fail.
Well, that, okay.
Our speaker that
So the next thing we have to look at is our truss. And our truss is this blue stuff right here. Now, if you've taken a geometry class, you're going to look, hey, that kind of looks like geometry. Oh, it is. And we use a lot of trig to calculate its load capacities and its stress and tension and compression, which we'll get into later. This is our truss. Now it weighs a lot too. It has weight too. The weight is determined, we go by pounds per feet. So how long is our truss, or how wide is our truss? So from this point here and this point here,
40, unless they're 5 footers, and it's 20.
This is what's called our span. Okay, this is our span. And in this case, our span is 40 feet.
Okay, thought so.
So we have 40 feet of truss. Now, different truss weighs different amounts. In this case, our weight is 10 pounds for every foot.
Okay, so we're 400 pounds.
So we do some simple multiplication. And this calculation is real easy because we're dealing with tens. So 40 times 10 is simply 400 pounds. However, remember, we're going to multiply, we're going to add another 20%. So 400 pounds, again, multiplied by 0.2. Okay, so that's 0, 0, 8. Move the decimal over to there. It's 80 pounds. Now, we take our 400 pounds plus our 80, and we add them together, and that's 480 pounds. Now, that's our truss. Okay, now this is the weight of our truss with our safety calculated into it. So our truss plus our lights, that's going to equal our load. All right, so our truss is 480. Our lights, remember, were 720.
720, okay.
0, 0, 1. 4 plus 1 is 5, plus 7 is 12. So we're looking at 1,200 pounds of our load. All right. We have 1,200 pounds. So right now we're going to get a good guesstimate that each of our motors, which are these guys right here,
highlighted in red,
here, and here, needs to lift 1,200 pounds. However, there's two of them. So we divide 1,200 divided by 2 is 600. Now that's that's just a rough idea right now. The question is this is what do we need 600 pounds motor capacity? We're probably going to need more, because this is just the simple first line of math of calculating the total weight. And we can do this in this case because everything is symmetrical and we know each motor is going to be pulling the same amount of weight. But let's go a little further.
Okay.
To do this correctly,
see, this is the shit I gotta learn.
Let's take a look at some weights that are off-center and the calculations that go into them. In one of the other videos, we calculated the full load of a truss very easily because it was a UDL, or uniformly distributed load. And that gave us our first calculation to determine the weight for each motor so that we could spec the right gear. But not all weights are even. In many cases, the weight is not even. So let's take a look at an uneven calculation to determine, so we can determine how much weight each motor is going to carry. So we're going to call this is our 8 feet. We can calculate it the other way too. To our load. In this case, because remember our truss to here. In this calculation, this span. Let's remember our motors. They're lifting things up. These little red guys here. They're lifting. Well, this is what we want. We want things to go up. Okay. So the distance between these two is going to be the motor span to here. In this calculation, this span is 30 feet. So this is very important because all these calculations are based upon from a lift point to our load. This is our load here, which is our light. And remember from the other videos, our load is 90 pounds. Okay? So we know our span is 30 feet to the lift. And we know currently from a previous video that each of our motors are currently carrying 240 pounds. Because remember, our truss we calculated at 480, and we could easily split that in half because it's splitting the load evenly. So we know we need to lift at least 240 pounds per motor plus this offset weight. What we're going to do next is we need to know the distance from this lift point to our load. In this case is 22 feet. And we're going to call this distance 1. Okay? This distance 1. Okay? Now, from this motor to our load, we know is going to be 8 feet. And we're going to call this distance 2. And that's a real simple, quick calculation. We have our span, our motor span, which is 30 feet, minus our 22 feet is our 8 feet. We can calculate it the other way too. We can go 30 feet minus 8 feet. We'll leave 22 feet for the other distance. So let's calculate the load or the tension on lift 1. Up here, how much is our motor number 1, our first guy here, what's he carrying? Well, load 1 is calculated by taking the load, our weight, we take our load, okay, so load 1 equals our load multiplied by distance 1, and then we divide
by distance 2.
By the span.
Okay, by the span.
Okay, so lift 1 equals our load, which is 90 pounds, times distance 1, which is 22 feet, and that's divided by the span of the lift, which is 30 feet. Okay, now since these are both feet, 30 feet and 22 feet, we can cancel this out, and that'll just give us pounds. So what's the first thing we do? Well, let's multiply 90 times 22. Take 90 times 22. That's 0. That's 180. This is 0. And then we add there, that's 0. Okay, we add these together.
28, 2980.
That's 1,980.
And then you divide it by 30.
So L lift 1 equals 1,980 divided by 30. Okay. Well, these are zeros. We can cancel these out right here, which is the same. Lift 1 equals 198 divided by 3. So lift 1 equals 3
that's like 65 and some change.
into 198.
65.6.
Okay. 3 doesn't go into 1, but 3 goes into 19 6 times for 18.
Or 60.
Okay. Which leaves 18 pounds. All right, so that's 66 pounds.
66. Done.
Is this our final answer? The answer is no. So 66 pounds of our 90-pound weight is on lift 1. Okay. So let's add.
Lift 1 is doing 306 pounds.
So lift 1 is carrying our 240 pounds plus 66 pounds of the first light. So that's 6, that's 0 and 1, so that's 306 pounds. All right, so now in this example here, our motor is carrying 306 pounds. That's lift 1. In our next video, we'll calculate lift 2.
Huh. Cool.
So in the last video, we calculated that load 1. So how much is lift 2 carrying? Of 2 is holding 264 pounds.
It is. Okay.
And as you can see, there's a significant difference. There's about a 36 pounds. Well, here we simply subtract. These two numbers, this is 66. In this video, we're going to calculate weight and force. And the reason we're doing this is so we can determine which equipment we need to make sure that our production is lifted safely. But also these calculations are our first line of safety to prevent an accident. Okay, so as we can see, this truss is in our uniformly distributed load, which will make things easy. But let's take a look at the actual elements so we know what we're talking about here. All these guys down here, this is our lighting equipment. Okay? And each light has weight to it. In this particular case, so we need to know how much does our lighting weigh? And we'll just do some simple addition. So our lights, in this case, weigh 75. Calculate the weight of truss.
Okay. It's the only thing I don't really like about this mode. Like, it tweaks out quite a bit.
In this first introduction to lighting,
Geegan. Ooh, it's already there. Let's go.
So the D to D ratio has to do with the diameter or distance of the load that you're picking up. Say we're picking up a piece of pipe that's 12 inches in diameter, okay? And then we're using a 3/8 sling, 3/8 chain sling to be able to pick up that pipe. So 12 inches divided by the 3/8 chain sling size that we're using will give us our D to D ratio. So we always want to make sure that, say, you know, we're picking up that load that's 12 inches, 24 inches, 36 inches, and going around with a sling that gives us the proper D to D ratio, which generally for a chain sling is going to be 6. You always want to be above 6. But that goes for all slings. I mean, so often working with wire rope and going around items, wire rope D to D ratio is extremely important to make sure that you're getting the full capacity of whatever sling angle you're using or sling that you're using. For nylons or synthetics, it's not really so much a concern. It can be a little bit, but for the most part, wire rope and chain is where you're going to find D to D ratio being of supreme importance.
I've been getting a lot of questions lately about vertical bridles versus baskets, or rope, chain, straps, any of those kind of things, when you have a single strand versus if you double it up. And the principle is that doubled up is twice the strength of vertical. But there's a lot of redneck inside of everybody that sees this single point of rope here where the load's connected, and they say to themselves that it can't be twice the strength because there's only a single piece of rope at that connection point. But what we're going to do today is talk about it. We'll talk about the physics of it, and then we've got a demonstration to show and prove that it does double the strength of it. So what I want to articulate here is that if I have a vertical strap or a piece of rope that's single, if I pull on it, every point in the rope, from this point all the way down to where it's connected to the load, here, 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 every instance in that rope has to have the same tension in it. It can't be different somewhere else. It has to have equal tension. And so if I apply a 1 kilonewton force to it, it's 1 kilonewton here, 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 here. It doesn't matter. It can't be a different tension throughout the rope. I hope everybody can see that and understand that. Same as if I deflect the rope slightly. The tension has to be the same throughout the rope, all the way from where the load input is to where it's being pulled on the load. The tension has to be equal throughout the whole rope. Where we have a single strand, if you're dealing with chain or you're dealing with a wire cable, that's what's called a vertical bridle. But if
sometimes people consider load charts to be a little old-fashioned. They're very necessary for us, even if you have a crane that has a load moment indicator or a rated capacity limiter, because if you're in a situation where you have a malfunction of your LMI system or you have a problem with the rated capacity limiter, you can go back to your load chart if you're in the middle of a job until such time as you get the system repaired. Also, a great number of older cranes are not equipped with a rated capacity limiter or any sort of an electronic scale, so there has to be some sort of a graphic way to calculate what the capacity of the crane is at any specific load radius. First of all, we want to talk about load radius. There's
Hi, I'm Tom DeSue, and I work for the SlingMix Group. And today we're going to work on D to D ratio on our rigging gear. And it varies from piece to piece. So we're going to go through each type of gear to do it. We're going to start off with single part wire rope. We're then going to go to 3-part wire rope, to 9-part wire rope, to synthetic web slings, synthetic round slings, in particular single path, then twin path, and then we'll also talk about blocks a little bit as well. So D to D ratio originally started with wire rope. It started out with mainly single part wire rope. And what D to D ratio is the diameter of curvature around which a wire rope sling is bent affects its capacity. So the more we bend a wire rope around an object affects how the capacity is. Now with a single part wire rope sling, it's 25-to-1 D to D. And the 25-to-1 is 25 times the diameter of the wire rope. So whatever the object is divided then by the wire rope, and that's how you get your D to D ratio. Single part is 25-to-1. If it happens to be less than 25, you're going to have to then derate per the chart for what that percentage is. And it's simply of taking the diameter of the object, dividing by the finished diameter of the wire rope sling. That'll give you your percentage, and you look for that percentage on your chart, and you just take your working load limit for that in your straight line configuration, then times it by that percentage, and that'll give you your new working load for that wire rope. When it comes to 3-part, and the 3-part is multi-part wire rope, and the idea is you get 3 smaller component parts, which will give you a finished diameter. Now the D to D ratio is different for 3 parts. For in the body that you see here, it's 5-to-1 compared to 25-to-1 in a single part. And in the eye, it's 1.5 times to 1, 1.5 to 1 for the D to D ratio, which is a really, really good D to D ratio. Now there are multiple part wire rope slings. You can have a 3-part, a 4-part, a 5-part, a 6-part, a 7-part, an 8-part, and a 9-part. At SlingMix Group, we typically do 3-part and 9-part. Now this is a 9-part gator lathe, and it's, again, the diameter of curvature around which the rope sling is bent affects its capacity. Now with this one, it has a 5-to-1 D to D in the body, but this is different. It's a parallel lathe eye right here, and this has a 1-to-1 D to D ratio, which is excellent. And most multi-parts don't have that. And when it comes to other multi-parts that aren't SlingMax, you need to check the manufacturer's recommendations for it because they do differ. SlingMax recommendations are 5-to-1 in the body for 3 or 9-part. For 3-part triflex, they are 1.5 times to 1 in the eye, and for a gator lathe or a 9-part, it's typically 1-to-1 in the eye. Chain also has a D to D ratio. When I went to school in early
Welcome to Strider Trees. Today we are talking about forces. It's going to be a little bit of a nerdy conversation. We're going to break down vectors and torque and all this good stuff so that you can better understand how to take advantage of the strength of the tree so we're not breaking out canopy anchors that our lives depend on. Today this one's sponsored by Edelrid North America and the Academy Trained. I'm here in the Academy down in Santa Rosa where they do all forces are always applied in a direction. It's called a vector. A vector is a force in a direction. And in physics, we will describe that generally as with an arrow, right?
Okay, right.
And
This experiment is a small-scale version of something I do on a much larger scale if I'm giving talks. The large-scale version has a piece of rope, and I get two people to pull the rope as hard as they can horizontally. And then I get somebody else to push down the center of the rope with 1 or 2 or 3 fingers. And they can do that quite easily, but they notice that as they try and push it further and further down, it gets more and more difficult. Now here's the small scale version. I've got 2 weights on the 2 ends of the string here. They're both 2 newtons. And I have a 1 Newton load in the center. And you see the 1 Newton pulls down the center quite easily. And the important thing is that the center is such that the angle is approximately 10 degrees to the horizontal. That's the whole important point. It's the angle, the component of the vectors. So these 2 forces, the 2 newtons, combined, the cosine of the angle there, that's 80 degrees, plus that one, 80 degrees. So 2 times 2 newtons times the cos of 80 degrees balances the 1 newton. Just repeat that. 2 times 2 newtons multiplied by the cosine of 80.
Wi-Fi just shit out for a minute, huh? 'Cause why not? Sick. Big bet. Okay.
Hey folks, it's Ozzy here. Today I'm going to waffle on a little bit about load factors and try and explain what they are and how you can figure them out for yourself. So what is a load factor? A load factor is a factor that needs to be taken into consideration when we're using any part of lifting equipment. Alright, so everything's got a rating. It's rated to 100% of its working load limit, WLL. So when we pass a sling around an object, or if there's 2 slings and they have a bit of an angle, these factors come into play. We're going to talk about angle factors and rev factors. But let's have a look at something that we're all pretty familiar with. This backpack here. I don't know what this is rated to because I don't know straps. However, this strap, when it's used directly like this, is good for 100% of its rated capacity. Let's say it's good for 50 kilos. It's just a backpack.
I don't think this is gonna tell me much, but let's see.
Welcome to A4i TV. I'm Siobhan Colleen. This is the Build a Bridle series. Today's topic, wire rope drop. Words are hard, but it's okay. Sometimes the beams are ridiculously high. Rather than have ridiculously long bridle legs, wire rope drops are used to make up for the excessive height difference between the motor hook and the beams. Plus, it's a lot more pleasant to haul 80 feet of motor chain with a 20-foot wire rope drop rather than 100 feet of motor chain. Motor chain for a 1-ton capacity hoist weighs about 1 pound per foot. You do the math. We're doing this in the air for demonstration purposes because it's easier to see. But all of this gets built on the ground before getting sent to the uprigger. Rock and roll basket, burlap on each
Always.
one, bridle legs all the way to the junction shackle. We've got our wire rope drop. It just goes where the motor hook would normally go. It's almost like with each video, we're just replacing where the motor hook used to be. And then all the way at the end of your wire rope drop, we connect our motor hook. Pretty straightforward. Or shall I say, straight down? That's actually hilarious. Straight up though. Thanks for watching. Give this video.
Okay, that didn't teach me nothing I didn't already know. Age, like. Let's see. Yeah, this was really good. That was a good ass video. Yeah, this one.
Hello, I'm Danny Bishop, Corporate Director of Training for the Crosby Group, and I'd like to welcome you back to another episode of Ask the Expert. Today's question comes to us from Carl at NIBSCO. Carl's question is, if you're lifting a non-symmetrical load with center of gravity not in the middle, and you're lifting that load with multiple sling legs, can you base the slings and the rigging hardware on the calculated tension of the sling closest to the center of gravity? Well, to answer that question, let me first state that I do like the idea of basing the sling capacity on the sling closest to the center of gravity, because that's the one, in this example, taking the greatest share of the load. However, I can't say that that is the correct path to take in all material handling activities around the world, because we do run into some exceptions. I've got a simulated load here. Let me maneuver it in so you can see it better. It's good for explaining complex topics and even simple rigging topics at times. Let's take a look at this and notice that we have shorter slings over here. These slings are the slings closest to the center of gravity. Actually, I have weight added where my hand is. I'm inside the load. These slings are longer, and they're seeing the lighter side, or filling the lighter side of the load. With eye bolts being our connection points, we have to realize a few things. First off, when we're using shouldered eye bolts, such as here, eye bolts lose the majority of their strength in the first 45 degrees of angular loading. And if you take a look, the angle of loading is pretty minimal on these eye bolts closest to the center of gravity. The angle of loading on the eye bolts away from the center of gravity, as over here, this is more drastic. So if we don't do a careful analysis before the load comes off the ground, you may accidentally undersize the eye bolts that you need based on the angle, even though the eye bolts might be these farther away from the center of gravity. In fact, we may even need to possibly use swivel hoist rings instead of eye bolts at some of these connection points. In closing, let me just state that that's just one example. We do
you know
run into
anything
other
about rigging,
exceptions, such
by
as
chance?
sometimes the pick
Coming
points
to
are
you.
not on the same plane. Sometimes we have
Do you rig, I guess?
pick points not on the
Who in
same
here's a
level.
rigger?
So let's just make sure that a qualified person analyzes all the slings, all the rigging hardware, all the connection points, especially when we have non-symmetrical loads with center of gravity not in the middle. Good question, Carl. And we hope to see each of you back on another episode of Ask the Expert.
Alright, well, I mean, that was... Sorry, let's see. This might be good.
We're now ready to go to work. Please make sure you have your Crosby User's Guide for Lifting available. As you review Panel 1, remember that learning does require hard work and that excellence is achieved by working hard on the correct skills. Rigging skills require this same effort. We hope that this training program on our User's Guide for Lifting will assist you in your efforts to achieve excellence in rigging. Although rigging has been around for centuries, overhead lifting is still a special event. Risk is created every time we lift a load off the ground. Special tools, special methods, and a special mindset are required when rigging. Avoid rigging practices that create risk, even if you've done it that way for 20 years. To Crosby, risk management requires that the risks be reduced by concrete steps that have an impact from the manufacturer to the product user. Training and formal product warnings are major tools that Crosby has made available to support this effort. Training videos and comprehensive product literature are also available.
The basic requirements for rigging safety can be found in the OSHA standards, Title 29 of the Code of Federal Regulations, or 29 CFR. The basic OSHA sections that apply to construction are in Part 1926.250 and .251, known as Subpart H, 1926.753, Subpart R, and 1926.1400, also known as Subpart CC. For industry, include 1910.184, slings.
The rigging fundamentals required by OSHA includes the inspection of rigging gear, the need for a competent rigger, loading all rigging gear within the working load limit, and proper storage when not in use. OSHA also states eyes in wire rope bridles, slings, shall not be formed by wire rope clips or knots. Wire rope clips are utilized in many applications. These include suspension, guying, tie-down, dead-ending of blocks and winches, and in conjunction with wedge sockets. ASME B30.9 states, only use clips to form eyes on slings or bridles when the application prevents the use of prefabricated slings or for specific application designed by a qualified person.
Both OSHA and ASME B30.9 require all slings to have permanently affixed identification. Please refer to the OSHA and ASME standards for complete information.
As we continue to develop the list of key questions that need to be answered when rigging, it is useful to review common rigging problems. Keep in mind, most serious accidents result from a combination of problems. Compliance to OSHA alone is not sufficient for best rigging and good risk management. Compliance with ASME standards and the manufacturer's recommendations are critical as well. There are several words we frequently use when we describe the capacity of rigging gear. Working load limit is the maximum load that the gear can support with an inline pull. Proof test is a test to determine material or manufacturing defects. Ultimate strength is the load at which the product fails or no longer supports the load. Design factor describes the theoretical reserve capacity of rigging gear. Synthetic slings, wire rope slings, and their fittings must have a design factor of at least 5 to 1. Chain slings and their end fittings must have a design factor of at least 4 to 1.
Working load limit, or the maximum force a product is authorized to support in general use. Ductility, or the ability of an item to deform in an overloaded condition, thus giving warning before ultimate failure. Fatigue resistance, or the ability of an item to withstand repeated applications of a load. And toughness,
or the ability of a material to resist fracture.
When rigging is evaluated, the special nature of lifting is clearly seen. This special nature is the result of the need to manage risk. When riggers enter the world of lifting, they must always remember that the requirements for lifting are very different from other jobs. Some of these special requirements include: 1. Competent person is required. 2. Proper equipment must be used. 3. Must inspect equipment. 4. Maintenance requirements must be met. 5. Knowledge of proper application is essential. There are several world standards for rigging hardware. Crosby products are generally designed to the European CEN performance standards. These standards require performance testing of properties that include ductility, fatigue, and toughness. The world standard for quality assurance systems is the ISO 9000 series. ISO 9001 addresses
You're going to screw it in till it's tight and then back it off 1/8 of the turn. That way, when you lift the load, it doesn't get too tight, right?
No. The proper way to use a shackle,
Technically, no.
You would take the pin, and this would be a screw pin shackle. You take the screw pin shackle, you tighten it, hand tight, you leave it. That's as far as you go. You don't want to back it off, as you actually leave a little bit of a gap there. It might be only a couple thousandths. But what ends up happening is a lot of times when people pick things up with a shackle, the load might go to one side or the other side. This, we call this the spread, this opening. When that happens, you could potentially bend this ear out. And the reason why that happens is because you've given it somewhere to go. If that gap was gone, well then this gap, this spread can't get any bigger, even though you're putting weight on one side of the ear or the other. Backing it off is totally a myth.
You're going to screw it in till it's tight, and then back it off.
I get it. We always back it off because we gotta take it down like 6 hours later.
In this video, you will learn some basic rigging devices, as well as some basic rigging techniques, and how to safely apply them in the field.
In the world of rigging, there are 3 basic hitches: the straight leg vertical hitch,
Yeah.
the choker hitch, and the basket hitch. Regardless of the type of sling or hitch being used, the user must ensure that the sling and rigging hardware have working load limits that exceed the actual loading imposed on the sling and the rigging hardware attached. Also, crane operators and riggers should be aware that by moving a load harshly, you can easily double the loading on the slings and hardware attached.
Synthetic or steel-based, web or round, wire rope, chain mesh. Slings are an essential part of any lifting and rigging situation, but can be confusing, and this confusion can create an unsafe situation on one of your job sites. So what sling is the right one for the job? From materials, shapes, and weight ratings to most common uses, we're going to cover the what's what on slings.
Everything has
built
a
for
rating,
any
so if you
task. There
don't
are 5
know,
common
look
types
and
of
read.
slings found
See
on
those
job
tags,
sites.
read them.
They are broken into 2 main categories: synthetic and steel-based. Let's start with the most common types of slings. Synthetic. There are 2 main types of synthetic slings: web and round. We'll start with the synthetic web sling. Synthetic web slings are flat synthetic lifting products made of webbing material and feature fittings like flat or twisted eyes on each end. Synthetic web slings are inexpensive, lightweight, durable, and strong, as well as flexible, easy to handle, and can adjust to irregular loads while maintaining a secure grip. Because of this, They are the most versatile and widely used multi-purpose lifting slings. Synthetic slings are exceptionally resistant to rot or mildew and are not normally affected by grease or oil. They can also be fabricated with wide load-bearing surfaces and are still easy to rig and handle. Most web slings are available in thicknesses from 1 to 4 ply and have a capacity from 950 to over 200,000 pounds. Synthetic web slings are broken into 2 main groups, nylon and polyester. Nylon web slings come in either regular or heavy-duty webbing and will stretch approximately 10% at the working load limit. They can also be used in alkaline environments. Nylon slings cannot be used in acidic environments or around any type of bleaching agent. Polyester web slings are the most popular, cost-effective sling available and come in standard and heavy-duty webbing and stretch approximately 7% at the working load limit. These slings can be used in most acidic environments or when bleaching agents are present, but they cannot be used in alkaline conditions. They also are non-sparking, non-conductive, and safe to be used in explosive atmospheres. To improve either nylon or polyester slings' durability, wear pads are common to protect against cutting, puncturing, or abrasion. Web slings, either nylon or polyester, are used in nearly every industry and for lifting everything from rocks for landscaping to pipes and beams for skyscrapers. Now let's talk about synthetic round slings. Synthetic round slings are most commonly made of a continuous loop of polyester yarn covered by a double-walled tubular polyester jacket and are color-coded for easy identification. They are especially useful for lifting tubes, pipes, or materials that could be damaged with other rougher slings. Round slings can be used in chokers, basket, or vertical hitches. Synthetic round slings normally range in body diameters from 5/8 to 3 5/8 inches, but custom slings are also common. Synthetic round slings have lifting capacities from 2,600 to over 180,000 pounds. Some of the advantages of round slings are the jacket protects from corrosion, abrasion, and UV degradation, as well as securely gripping the load. The jacket also resists moisture absorption, rot, and mildew, and their low stretch makes them great for lifts with low headroom. Next, we're going to cover steel-based slings. There are 3 types of steel-based slings: chain, wire rope, and mesh. This is an alloy chain sling. Alloy chain slings are the most durable of all sling types. They're well suited for extremely heavy or rugged loads, as well as high temperatures that would destroy other types of slings. Alloy chain slings are made up of 4 parts: master link, ID tag,
chain,
sling legs,
which is the chain,
and lifting attachments. Each of these parts has a few different options depending on their intended use. Like wire rope slings, alloy chain slings can have anywhere from 1 to 4 sling legs. Alloy chain slings are easy to inspect, can be repaired by replacing individual links or link segments. After proof testing, they can be recertified to be used in the field. They're also easily adjustable, which can be done by removing links or link segments. Alloy chain slings can be found in 9/32 of an inch to 1.5 inches. And
so, itchy. If there's a bad chain, you have to decommission the whole chain. You have to go retest it. If you want to leave it at that length, you still have to go retest it, I'm pretty sure. But if you fix it, you have to retest it and get it recertified in order to use it again. Otherwise, just buy a new one.
And have a lifting capacity between 3,500 pounds and over 90 tons. While these slings are perfect for the most intense jobs, they are typically more expensive, weigh more, and have a tendency to damage the load. Alloy chain slings are mainly used when other slings are likely to be damaged, like in foundries, steel mills, and heavy machine shops. Up next is the wire rope sling. The low cost and ease of use make wire rope slings popular among crews, and they excel in lifts where protecting a fragile load is essential. Typical wire rope slings consist of 4 main parts:
that's what I use a lot.
Individual wires, multi-wire strands, a fiber or steel core, and lubrication. The individual wires are braided into strands, which are then laid around a core in a helical pattern to produce the sling. There are different types of cores, strand patterns, and lays depending on the sling, meaning that many wire rope slings are designed specifically for lifting certain materials
or lifting in certain situations. Overall, these slings are more durable than synthetic slings and more cost-effective than chain slings. They have the lowest cost per ton of lift of all slings and are known for their strength, ability to bend without distortion, and to hold up against abuse or abrasive wear. If your wire rope sling does get damaged, the master links and hooks can be reused, which helps cut down on replacement costs. Wire rope slings can range from 1/4 of an inch to 3 inches in diameter and have capacities from 1,400 pounds to 153 tons.
Big as
Traditionally, wire rope slings
that's
are
over
used for hot materials,
300,000
crane or elevator
pounds.
wires, and general
1 ton
construction
is
where
2,000
loads aren't in
pounds.
danger of being damaged when lifted. They are mainly used in machine shops, steel warehouses, and other metalworking industries. In order for any sling to be used on a job
Concerts.
site, regardless of the type, they are required to have a legible and present safety tag. Any sling without this must be removed from service and replaced.
That doesn't always happen. I just want you guys
Shackles
to
are
know
commonly
that.
used to attach a sling to a load. A screw pin shackle, which consists of
Another name for this is clevis.
two pieces, the shackle bow and the pin, is often the shackle of choice in pick-and-place applications. Crosby shackles discussed in this video are manufactured with a patented quick check feature that incorporates 2 marks forged into the shackle bow at 45-degree angles from vertical on each side.
Right there and right
These
there.
quick check marks are used to quickly check the angle of a single leg hitch when the shackle pin is secured and the pull of the load is off vertical, resulting in a side loading circumstance.
Exactly.
These quick check marks are also utilized to quickly check the approximate included angle of a 2-leg hitch.
So this, I think it's on both, so yeah. that
Before
means it's
selecting
at
the correct piece
45.
of rigging hardware for your application, you
It's
should
right there
determine
and
that
right
the
there.
diameter or width of the rigging hardware being used is bigger than the diameter of the wire rope sling. An example would be,
That's a
if you're
tool that
using a 20
measures.
millimeter diameter wire rope sling, the shackle attached to the wire rope sling eye must be at least 7/8 of an inch or 22 millimeters in diameter. It is also worth noting that the European EN standard requires that the object in the eye of the soft eye sling be not less than twice the nominal diameter of the wire rope. Once the shackle is connected to the sling, the shackle is attached to the load with the screw pin in contact with the connection point on the load, as shown. The screw pin is then rotated to a minimum of hand tight into the ear of the shackle body with full thread engagement before lifting or movement of the load
That is technically the right way to do it.
begins. The load should be centered on the shackles to prevent side loading, and
This is the load. Okay. It is center on the load down here. Okay.
the screw pin must be
And
tightened
it's
before
centered
each pick.
on the pin here. This, it's hard to make sure that it's centered on these because of the way it's pulling. And that's fine.
The rigging triangle is a key consideration when making connections to loads and load hooks. The rigging triangle is formed anytime 2 or more slings are connected to a load and load hook. Whether the slings are chain, wire rope, or synthetic, the best practices are based on the same principles. Focusing on the horizontal sling angles formed in the rigging triangle highlights several best practices that are very valuable to the rigger. It is important to remember that as the rigging triangle becomes flatter, the horizontal sling angles become smaller. As the horizontal sling angle becomes smaller, even though the lifting load remains the same, the crushing loads
force
increase.
is
The
different,
sling
exactly.
tension is the result of both lifting and crushing. This means as the sling angle becomes smaller, the sling tension and the load at the load connections increase, and the crushing forces pulling the slings toward the CO be reduced by 50%. A single leg choker hitch is easy and convenient to use and can work well on simple, short loads, but it does not always provide the load control and grip needed for safe and effective
you
rigging.
see how not tight that is? You see that big space here?
Sometimes
Not great.
multiple leg slings
See how
choked
how much smaller that
on
is?
both ends of the load are
That helps.
required to gain the load control loads and bundles of materials like rods or pipe
are mid.
that require corners, protrusions.
It is important to point out that Crosby's general catalog. Used in side-loading applications when installed correctly.
Corners, protrusions, or abrasive surfaces in order to protect the sling from any damage.
Crosby screw pin and bolt type shackles, sizes 3/16 inch to 3 inch, can be used in side-loading applications when installed correctly with the pin secure and the direction of loading is in the plane of the shackle bow, as shown in Crosby's general catalog. However, a reduction in the shackle's working load limit is required when side loading occurs. It is important to point out that side loading of a round pin shackle is never allowed. It is secured by a cotter pin that could shear when side loading.
Yes.
When
shearing is when it breaks.
the direction of pull is vertical, perpendicular to the shackle pin, no reduction in the shackle's working load limit is required.
Zero reduction. Okay.
However, if the shackle is subjected to a side load of 45 degrees from vertical, the shackle's working load limit must be reduced to 70% of the shackle's rated capacity.
So if the shackle's rated for 10,000 pounds, it's not. Then that means is now rated for 7,000 pounds.
Thus, when a screw pin or bolt type shackle is subjected to a 45-degree side load, the shackle loses 30% of its published working load limit. If the screw pin or bolt type shackle is subjected to a 90-degree side load from vertical, the adjusted working load limit would be 50% of the shackle's rated capacity. Thus, when a screw pin or bolt type shackle is subjected to a 90-degree side load, the shackle loses 50% of its published working load limit. It is important to state that when a shackle is used as a collector ring to gather multiple sling legs as shown, this is not considered a side loading circumstance. When the slings are collected with the included angle not greater than 120 degrees, this would be considered a balanced load, and the shackle's working load limit would not require a reduction.
Using 2 slings in a true inline load, each side will see half the total weight. From the Crosby lifting guide, notice that for a 90-degree horizontal sling...
Okay. Let's see, what else we got? I mean,
when it comes to rigging, we're looking at the ASME B30 standards. A certification through a accredited agency such as the CCO, they will not train somebody, but they will administer a nationally recognized written and practical exam.
I mean, at this point, I just gotta read my books now. I don't think there's much I can really learn online. On YouTube, anyhow. Love this. 12 years ago. I think I want to...
We end up with the complete shear force and bending moment diagrams for the beam. That example was a fairly simple one, for cases with more complex loading. Drawing the shear force and bending moment diagrams can be more difficult. There are relationships between the applied loads, shear forces, and bending.
Shear force or shearing force works like this. As you can see, as I am cutting a lot of pieces of paper with a pair of scissors. A shear force is a force applied perpendicular to a surface, in opposition to an offset force.
Okay, I mean that's it, yeah. That's it. What else? What other content should I look up? 3-way bridles? I mean, I don't think there's much to learn here. I don't think she's gonna fucking teach me shit. Let's see.
So ayun mga sir, ito na tayo sa pangsunod nating topic, ang number of ng legs.
I can't listen to that. Never saddle a dead horse.
Wait.
I like these videos.
No! No!
I thought this video was going to be boring. How strong are swages on wire rope? I'm Bobby, and I have been working building challenge courses and zip lines for the last year. And we do a lot of connections like this. This is a zinc-plated copper sleeve, and you can use it to make an eye or to join two cables together. And you use a hydraulic crimping compression tool to force the material.
These tools are expensive as fuck.
They don't hold if you don't crimp them.
Apparently, that's an important step. Other than sleeves, you can use one of these U-clips to terminate your cable. And since horses were the main mode of transportation when cables started getting used, they said don't saddle a dead horse. But we'll get into that later.
This is a 3/8 cable. This is 7 by 19, which means there are 7 bundles of 19 little strands.
What's this rated to?
14,400 pounds.
That is crimped really bad. Let's find out how strong these are. We'll start with a control sample.
This is quite close to how the manufacturer of these sleeves recommends you do it. The exceptions from that are they would like a little bit more wire rope sticking out so they can be sure that it's entirely engaged with the sleeve. But on both of these, the wire rope goes all the way to the end of the sleeve.
Wow, sounded strong. Oh, it came out.
It's not that warm. Oh, that is.
We started to see some breakage here, and then it came out of the swage. When we were testing the swages for dog bones, like homemade dog bones, often we had failure here.
Yeah, breaking the crimp.
Yeah. This is the termination scheme that my company uses. They add an aluminum sleeve here. The main purpose of that is to ensure that there is enough tail sticking out, and it covers up the tail, which when crimped tends to splay out like this and gives lots of little sharp things that cut people as they go by.
So do you think that adds any strength?
We're going to test it.
Okay, that's why we're here.
I think we'll have a different failure mode than on the control.
That's less.
This is loud.
So our failure was in the first compression here of the aluminum.
Wow, it broke in the swage. When we tie knots and ropes, they break in the knots. When you pinch the crap out of a wire, imagine that. It breaks in the swage.
Very different result than the last test, but a very similar number.
Yeah, a very similar number.
What happens
Like
if you don't get all
500
the
off.
switches on there? We're going to test with 2 compressions.
This side has 3 compressions, and this side has 2 compressions and a little bit of a skirt. A lot lower. 15K and lower.
Yeah. So having less compression.
Do you
gives
see how
less
bad
strength.
that
It's
thing
still 10,000
slipped?
pounds. Slid out of the sandwich.
What happens if you only get 1 compression?
This one actually does look like a dress. I bet we're going to get less strength out of it.
Wow, 6,000.
That's a lot less. Broken gear. Ooh, ah.
I got 3 compressions here. They're done really badly. One is on the edge, and the second one is overlapping that, and the third one's on the edge, and I don't have all of the rope captured.
For being 3 crimps, that was bad.
Having 3 bad crimps is better than having 1, but having 2 good crimps was stronger. If you don't have a hydraulic crimper, you could use clips, or if you want adjustability. They have a saddle and a U, and there is a very common phrase across multiple industries on how to place these. Never saddle a dead horse. So this being the live load, this being the dead strand, and the saddle is on the live load. When these are compressed, it kinks the cable quite a bit because this is a fairly narrow bend radius versus the saddle. This will be our control, and then we'll see what happens when you break that rule. These generally get installed with a torque wrench. Cue all of the comments about using a torque wrench wrong. So if you'll notice here, this U has severely deformed the wire rope. I should deliver 80% of the rated load of the 3/8 cable.
But the sleeves will do 100.
The sleeves will do 100.
So this is your fixed eye end.
Yeah.
You tighten the crap out of it and then you use these.
Yeah, in a number of scenarios. Like, that's what you do for, like, a guy wire.
That's not bad, 13. Damn.
Wait, no! 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 It broke on the swage!
I thought this video was going to be boring. That's super surprising.
The other ones we got 67, 65, and here we got 60.
It could be argued that I didn't fully bury that, but that's not what failed.
It didn't slip. That would have caused slippage.
Yeah, that would have come out if it wasn't fully held.
I wonder if this caused.
I have a carabiner that's rated for that.
It is crazy to me how much that's
13,000
I can see
pounds.
why you want to saddle the live horse.
Slow-mo?
We could review that. Yep, it broke where it looks like it broke. Imagine that.
You should call out with the slow-mo guys. I would love to. Email them for me. They don't answer my emails.
Harder to saddle the dead horse. All right, now let's saddle the dead horse.
Do you normally wear gloves when you do this?
I don't. I'm not pansy.
If you're a pansy like me, we've got gloves that should be $50 for $5 or $6 at hownotto.com, including a whole bunch of climbing, caving, canyon hardware, some of the best variety and the best prices. We don't do wire rope yet, though.
So you can see us starting to choke out the live horse here, and we've got the saddle on the dead one.
Oh, you guys should collab with that torque test channel. Have you seen the torque test channel?
I do like that channel a lot.
That horse was moaning.
I think started to compromise it.
Bobby, what gave it away?
We saddled a live horse. We had
Kinda wanna see
failure,
what they got
right
next
where
door.
you'd expect. It was getting close to our 80%. The concern with this is over a long time, it might compromise this more.
Then as one slow pull after you freshly do it.
Exactly. I really thought our cable clip failure
Yeah.
was going to be slippage. So we're going
Agree,
to have
100
the
bucks.
cable
Yeah,
foot
I mean,
connections.
these are regular
Hopes of
prices.
seeing them slip.
Not this, but this looks really nice.
Wow, that's a lot more
Oh
than
wow,
I
oh
thought.
wow, oh my.
That's really interesting. That is coming unlaid. I don't see any broken cables,
That whole
but we're
lay
not
is
far
fucked
off.
up. Holy
and then we
shit.
had failure at the first clip. It only
Okay,
clipped.
so their
That's
shit's a little more
not the
expensive.
failure
Actually,
was
no, I think it's the same price. That's the same
expecting.
price. Okay, because I got a
I
Grigger
thought it
Plus
was
as
going to
130.
slip. Based on our sample size of 1, having the second clip appears to support it a little bit better, giving you a higher result. 2 clips upside down, dead horse saddled, is better than having 1 clip.
Oh wait, they got rope?
According to our sample size.
They got rope?
So here's a beautiful hand-drawn chart of all of our data. And we actually tested a whole bunch of cable draws for permanent dog bones for climbers who leave these outside permanently.
And that's a dog
We got
39
some
a foot,
interesting
by the way.
results where they broke at the crimp and where they didn't. And you can go check out that video next.
Oh, that is a different result.
Hey,
That's
the
not
swage does
great.
matter.
But like this would be good for like scaffolding.
You know, gentlemen, I have a dream. That dream is to have...
Whoa, MMGHL. Hell yeah. Okay, that's a nice price for a little runner there. $10, $12. That's good too, these things. Fuck yeah. They got some good shit going there. Nice. Alright, let's see. This is something
Which
for you
way
guys.
should your shackle be
It
rigged to your
depends.
crane hook? Pin up or pin down? Great question. It depends.
There.
We need to first look and see what is going on below the hook. If more than one sling is attached to your shackle, first of all, you need to ensure that you are using an anchor shackle or bow shackle, the kind that looks like this, with a round bow. Second, the sling should be seated in the bow part of the shackle and not the pin. The lifting hook, or what is attaching your shackle to your crane or hoist, should be attached to the pin of the shackle. If it is only one sling attached and you're lifting in line, it can actually be done either way.
Yes.
Which way should...
There you go. What he's doing is making these a permanent. That's dope. I'd sit in the warehouse and do this all fucking day. Fuck yeah, I would. Yep, so now you gotta test them. Yep. Fuck yeah. Where the fuck's he working? Royal rigging. Where the fuck's royal rigging, huh? Where the hell are you located? I don't think that's in the U.S. No, didn't. Let's see what else we got. Yeah, I think this is
Figuring
good.
out the weight of the load that you're lifting is one of the first things you should do when you're writing your lifting plan. And in this video, I'm going to teach you how to do just that. Welcome back to the Lifting and Rigging channel. My name is Devin, and today I'm going to take you through one of the most important steps in your lifting plan, determining the weight of the load that you're about to lift. We'll look at the pieces of gear that you need to consider into the load weight, some simple methods of figuring out the weight in advance without doing any calculations whatsoever, and then of course we'll wrap up by working through the calculations and formulas themselves, both of simple and complicated shaped loads. So first, let's dive into what pieces of gear you need to consider into your plan. The total weight of the load must account for every piece of lifting gear involved in that lift, and I mean everything. The hook block, the lifting beams, the shackles, the lifting slings, and forgetting to factor the other pieces of rigging hardware means you're starting your lift with a flawed lifting plan. So let's look at a few different methods of determining the weight of a load.
I'm trying to find the fucking...
First, look to see if the weight is marked on the load itself. Sometimes manufacturers place the weight on the load for shipping purposes. So the weight may already have been spelled out and calculated for you. So if you can find that, it can guide you to the right rigging equipment for that pick. Second, look for engineered prints or design plans. Product prints and engineered drawings of the load may indicate the final assembled weight of that load. And it might even help you find a few anchor points that you didn't even know existed. You can also review the bill of lading or shipping documentation. If the load that you're about to lift was shipped or transported to your location, there should be some type of weight information on that shipping paperwork. It had to go on that semi-truck, they had to count for that when they were driving, so you might already have that covered.
Exactly.
If the load is a product or piece of machinery, the weight of that load may be indicated on either the paperwork that was provided by the manufacturer, any information on the manufacturer or distributor's website, or the product specifications in a catalog or product brochure. Those are all good reference points to start. There are a few times when you can add other devices into your rigging that can provide a readout and determination of the load weight when it's lifted slightly off the ground. Now, these devices measure and display the weight of a load in a few different ways, and some of the more advanced ones, probably the more expensive ones, can even send the readout to handheld devices or remote workstations to help gather the correct load weight before you make your lift. And if none of those options work out for you, then it's time to figure out how to calculate the weight of the load all by yourself. So let's look at some calculations and some formulas. So a lot of these formulas you've probably already heard of when you were going through school. These are just refreshers. So determine the volume of a load. For a rectangle or a square specifically, volume equals length times width times height. For a hollow cylinder, it's a little more complicated, because volume equals 3.14 times length times the wall thickness times the diameter minus the wall thickness. For complex shapes, in some instances, imagine the entire object is enclosed in a rectangle, and then calculate the volume of that rectangle. Or you can break that object into two or more smaller rectangles and then calculate the weight of each part and then add them together. Step 2, determine the weight of the material you'll be lifting. You can use a material weight table to figure out the pounds per cubic foot of material you'll be lifting. Step 3, determine the weight of the object. multiply the approximate pounds per cubic foot of the material times the calculated volume of the load to get the weight of the object or the load itself. All right, so now that you know the steps, let's calculate the load weight of an aluminum block that's 6 feet long, 3 foot wide, and 4 feet tall. You start with step 1. You gotta determine the volume of the load. And again, volume is length times width times height. So 6 times 3 times 4 gives us the volume of 72 cubic feet. Step 2, determine the weight of the material you'll be lifting. Using this table, we see that aluminum weighs 165 pounds per cubic foot. Step 3, determine the weight of the object. Multiply the volume of the load, 72 cubic feet, by 165 pounds per cubic feet, which gives us the load weight of 11,880 pounds, or 5.94 tons. This next example is going to be a little bit more complicated, so we're going to slow it down a little bit because there's a lot of different phases to get through this. For this example, we're going to look at a steel pipe that is 8 foot long, has a 3 foot outside diameter, and a wall thickness of 1.5 inches. As always, you start with step 1. You determine your volume, and it's a little trickier since you're using feet and inches in this calculation. So the formula is volume equals 3.14 times length times wall thickness times the diameter minus the wall thickness. And so before you can even run this calculation, you've actually got to convert your inches into feet and then provide it. And so 1.5 inches is equal to 0.125 feet. And now that you have those all converted, now you can actually calculate your volume. So 3.14 times 8 feet times 0.125 feet times 3 feet minus the converted 0.125 feet reforms your calculation as 3.14 times 8 feet times 0.125 feet times 2.875 feet. And that gives you a volume of 9.03 cubic feet. And again, that's more complicated, but it's important that you understand the steps and you take your time as you go through them. Step 2, use the table again to find the pounds per square foot of steel, which using our table is 480 pounds per cubic foot. Now, you can perform your calculation. 9.03 cubic feet times 480 pounds per cubic foot gives you the load weight of 4,334 pounds or 2.17 tons. For complex shapes, the goal is to simply take a complicated shape and make it simpler by breaking it into smaller, more understandable pieces. And so for us, this example, we're going to look at how to calculate the load weight of an irregular shaped concrete block. First, the goal is to break down and separate the two objects into normal rectangles and then to calculate each section individually and then combine them. And so what we've done is we've broken them into a top part, which is 3 feet by 2 feet by 4 feet, and a bottom part, 3 feet by 2 feet by 9 feet. And then your steps are the same. Step 1, determine the volumes. The volume of the top is 4 feet times 2 feet times 3 feet, which gives you 24 cubic feet. The volume of the bottom is 9 feet by 2 feet by 3 feet, giving us 54 cubic feet. The total volume is volume 1 plus volume 2 equals the total. 24 cubic feet plus 54 cubic feet equals 78 cubic feet. After doing that, you can move on to step 2, determining the weight of the object itself. Using the table again to find the pounds per cubic foot of concrete, which using our table is 150 pounds per cubic foot, we can continue our calculation. So take your 78 cubic feet times 150 pounds per cubic foot, and your complex concrete shape is approximately 11,700 pounds, or 5.85 tons. Like anything, learning to apply these formulas will take time and practice. And so to assist you, we put together this load calculations pocket guide. Save it.
What a fucking genius.
Your phone, save it to your computer, use it for reference anytime you need it. You can also grab our lifting and rigging best practices infographic. This is another tool you can use to ensure that everything from operator training to environmental conditions have all been factored into your lift plan before.
Lifting rigging channel, okay. Yes. Do this again.
Hey guys, welcome to Ranger. Lifting is a dangerous business and understanding how to safely lift a heavy load is essential. In this quick video, we're going to talk you through sling leg tension. We're going to explain what it is and show you one of the most common mistakes that people make when determining the working load limit of a chain sling. Let's say you have a 10-ton object to lift and you go and grab a chain sling and you hook it up. This particular chain sling has been rigged at 90 degrees. As the load is lifted, there is 7 ton of force placed on each leg of that chain sling. But what happens when a shorter chain is used to lift that same load? This shorter chain has been rigged at 120 degrees, and you'll see that as the load is lifted, the amount of force on each leg has now increased to 10 ton. And in the case of an even shorter chain, rigged at 160 degrees, the force triples again. The common mistake that is made is that people think, I've got this 10-ton load to lift, I'll go and grab that chain sling and can lift 10 ton. But they'll go and grab a chain that's too short. They'll lift the load anyway, and the chain will stretch and it could even break.
It will break.
Consider that as
that,
the,
right
as
there,
the angle gets
that
bigger,
broke.
the sling leg tension increases and the load essentially becomes a...
Okay, that's good.
This is the last video in a long day of making videos. This will be the last video that we have that has anything to do with sling loading and sling loading calculation. And for me, this is the most important of all the videos that we've done on sling loading, because this is how riggers actually do it. This is how crane operators and engineers that are doing the lift plans, this is the method they use to calculate sling loading. The other videos that we spend a lot of time on, those are important also, but just really they're just important for the CSP exam or the ASP exam if you end up taking that. But this is how it's done. They're important also, but just really they're just important for the CSP exam or the ASP exam if you end up taking that. But this is how it's done in the real world and real world rigging lifting operations. But let's go ahead and take a look at the rigger's method. And that's not something I made up. That is what it's called in the construction world and in the heavy lifting world, the rigger's method. And this is it. This formula right here is it. It's really simple. It's really simple. It's the load weight divided by the number of sling legs times L divided by H. And L is the length of the sling leg, and H is the height above the load, or more precisely, the distance from the pick point level to the hook. That's it. That's it. Again, L divided by H is sometimes referred to as the load multiplier or the load angle factor. You'll run into that terminology. Now, I do need to say a little bit more about the pick point level. Again, height is the distance from the pick point level to the hook. If you end up in a situation like this, you don't go all the way from the hook down here. You just go to pick point level. This is going to be your H if you run into this situation. And there are some odd-shaped loads that you may run into occasionally where this is the situation. And another situation you may run into is you're making a pick with rigging that has legs of different lengths. That's a real world situation you may run into, but I'm going to save that for a full-blown rigging class. We're just dealing with the basics of the rigger's method in this video. Okay, so let's do a problem. What is the sling loading on each leg? This is our rigging diagram. We've got a twin leg sling. We got a load of 12,000 pounds. The long leg is 94 inches, or the leg of the sling is 94 inches, and the height above the pick point is 50 inches. 50 inches from pick point level to the hook. And here's our formula. Just plug everything in. We have 12,000 pounds. Plug that in for load weight. We've got 2 legs. Plug that in there. We've got 94 inches for the length, and we've got 54 inches for the height. Now we just do the math. Let me bring my calculator up here and do this simple math. And another thing about this method, you don't have to have a scientific calculator. Heck, you don't even have to have a calculator. Pencil and paper's really all most people would need to do these problems. A simple calculator just makes it easier. Okay. So we got 12,000 divided by 2. Again, we could have done this in our head, and that gives us our 6,000 here. Then we have 94. Gives us our load angle factor of 1.88. Now all we need to do is multiply 6,000 times 1.88.
Now put your close
and
to
I'll
10,
do it the long way
maybe
just so
like
you see what I'm doing. I could have taken a little shortcut there, but I won't. 6,000 times 1.88. 11,280 pounds. This is the loading on each leg of this sling in this rigging configuration. And an important point I want to make through each of these. I didn't hit upon this in the other videos where we talked about sine and cosine and the trigonometric methods. But once we calculate the loading on each leg of the sling, we need to make sure that the sling material and all connected hardware has enough capacity for this 11,280 pounds of tension. You're likely to have shackles, eye bolts, of course the sling body itself, either chain or wire rope. Normally it's going to be wire rope. All of that has to have at least 11,280 pounds of capacity because that's our sling loading. Again, a lot of people that don't know any better, you'll see this with small construction companies. They'll just take this 12,000 pounds, divide it by 2, and assume that there's 6,000 pounds on each leg. But because of the angle, because of the distance from the center of gravity,
they don't understand.
It's not 6,000 pounds of force that's involved here on each leg. It's all 11,280 pounds on each leg is almost equal to the load weight itself.
Per leg.
So let's look at another problem, another example. Again, these are simple. We'll do a couple real quick here. Then I'll make some additional points and we'll be done. Okay, what is the sling loading on each leg given this configuration? 70,000 pounds, 160 inches for this leg, 120 inches for the height. Plug everything in. Do our calculations. 70,000. Oh, I put in too many zeros. Hey, again, we could do this in our head, but it's a good idea to avoid doing too much in your head. The calculator, if you have it available, use it. It helps prevent mistakes. 35,000 over here. Whoops. Now we need to calculate the load angle factor, the load multiplier. 160 divided by 120. $3.50. That's how much force is at work within each leg of this sling. But again, because of the angle, because of the distance from the center of gravity. And we haven't talked about center of gravity yet in class, or we may have by the time you watch this video, but your hook should always be centered over your center of gravity. And the distance from the pick points to the center of gravity is a big part of why the force on the sling increases the way it does when it's at an angle like this, when you have multiple leg slings. Again, that's really a topic you'll get into if you ever take a more advanced rigging class. Top-notch rigging classes are going to be about 2 days. I said before 12 to 16 hours is what you're going to have into it. And the best rigging classes, you're going to put your gloves on and your safety glasses and go out and handle some rigging and hook up some loads. Just like on the previous problem, once we have our sling tension, we need to make sure that all of our rigging materials have enough capacity for that level of sling tension. Okay. One more example, and this one's got a little bit of a twist to it. Notice the measurements are in whole feet. Everything else up until now has been in inches. If you see a problem like this and everything's in feet, that's fine. Just leave it in feet. If measurements are in whole feet, you don't have to convert to inches. But go ahead and run through the math here. Let me back up. Okay, we plug in our 115,000 pound load weight, divide that by 2. Then we plug in our 40-foot length by our 35-foot height, plug those in. Now let's do the math on those. 40 divided by 35. That's our load multiplier or load angle factor is 1.14. 115,000 divided by 200, or divided by 2, sorry. $57,500. So we have 57,500 times 1.14. We do that multiplication, our sling loading in each leg is 65,714 pounds. And again, if the measurements are in whole feet, you don't have to convert to inches. But usually what you're going to find in the real world is it's not going to be whole feet, or it's not going to be whole inches. Or you may have mixed measurement. You may have 40 foot and 18 feet 7 inches. If you run into that, like we'll see in the next problem, you need to convert everything to inches. And we have 33 feet, 18 feet 7 inches, load weight 62,350. Go ahead and pop all this up here. Again, if measurements that you have available are in feet and inches, convert everything to inches. If it's in whole inches, fine. If it's in whole feet, fine. But when you have mixed measurements like this, convert everything to inches. And when we do this for this problem, we plug in our 62,350 divided by 2. 33 feet is 396 inches. Let me just double check that to make sure. 33 times 12, 396 inches. Then 18 times 12 plus 7, 223 inches. So our numbers are all correct here. Okay, 396 divided by gives us a load angle factor of 1.775, rounded that to 1.78. Then 62,350 divided by 2. 31,175. Multiply this times 1.78. We already have 31,175 in the calculator. I'm just going to multiply times 1.78. Enter. 55,491.5 pounds is our sling loading, the tension in each sling. All right. You might run into a problem like this or a situation like this. Again, I'm talking about a real world situation. You're getting ready to make a pick. The rigging is already attached and all the slack is hoisted out of the rigging. You need to verify the sling loading. But the top of the rigging is over 20 feet up in the air. Heck, it could be 30 feet up. And you don't have the rigging measurements readily available. Again, you should have in your rigging plan, but let's say you don't. You know, they're starting to make the lift, the slack's all out of the rigging, but you want to verify it. How do you do that? You can't reach up there with your tape measure if it's 20 feet or more. How can you take the measurements from the ground and use the rigger's method to calculate the sling loading? Now I've kind of given you a hint there with the L and the H. And here's what I do. Measure up 36 inches on the sling leg. Again, this is the sling leg. Measure up 36 inches on the sling leg. Make a mark. piece of chalk. You really don't even have to make a mark, but to be precise, I want to make a mark. And then from that mark, I measure the vertical distance to the pick point level. What I'm doing is creating a smaller version of the rigging triangle. And with this smaller version, it is in proportion to the larger rigging triangle. So with a 36-inch leg and whatever this is here, I can calculate the sling angle factor or the load angle factor without having to get a ladder out or get up in a man basket to do that. And it doesn't have to be 36 inches. It can be 24 inches up the leg and then straight down to the pick point level. But whatever you choose is fine. But this is how you can do this without, once it's already up in the air. One last point I want to make, and here we're getting into a little more advanced rigging math when we start talking about 3 legs and 4 legs and 8 legs, and you can have bridle slings that have 12 legs. I mean, that's very rare that you're going to have that many legs in a single sling, but it is possible. But let's say you have sling loading using sling loading for a 3-leg sling. Same process. In this case, we want to convert our 5 foot 6 inch and our 4 foot 6 inches to inches. We have a 3,000 pound load. We have 3 legs.
That's fucking easy.
3,000 divided by 3 is 1,000. 66 divided by 54 is 1.22. Our sling angle factor, load angle factor. Our sling loading in each leg is 1,222 pounds. But once you get more than 2 legs, it gets tricky. This assumes, what we've done here assumes that all legs are equal length and an equal distance from the load center of gravity, which doesn't always work out that way when you have more than 2 legs. It is entirely possible that one or more slings may carry a small amount or even none of the load. It is wrong to assume a 3 or 4 leg sling will have a capacity 3 or 4 times greater than a single leg. And if you're absolutely sure that all your measurements are dead on, you can use this method. But here's the best practice. This is what you're going to learn in a Crosby rigging class, other rigging classes. This is what you may not hear riggers talking about this because some riggers don't know any better. But rigging classes, more advanced classes, the best practice, 2 legs of a multiple sling should have enough capacity to carry the load. Don't depend on any legs beyond 2 because of the way the load can be balanced, the way the center of gravity can be configured related to the pick points. You could end up with one of these situations where one leg or maybe multiple legs, they're there more for balancing the load than for their lifting capacity. For this example here, this is what I would recommend if I was doing a rigging plan. Calculate the sling loading for 2 of these legs and make sure that each of the 3 legs has enough capacity for that calculation. If we recalculate this for 2 legs using these numbers, and I'm not going to redo this, but just trust me on this. You could do it yourself if you wanted to. If we recalculate this for 2 legs, we're going to find the sling loading to be 1,830 pounds in each of 2 legs. So make sure you use this as your starting point. Make sure that each leg, all 3 legs, has enough capacity to handle 1,830 pounds. And that's going to be the best practice that gives you the greatest level of safety in lifting when you have more than 2 legs in your bridle sling. All right, well, that's it for the rigger's method. That's at least all that I'm going to burden you with in this class. I do encourage you, if you get a chance, take a Crosby rigging class. Maybe eventually at NSU we will be able to do something that's the equivalence of a Crosby rigging class. But again, it's 12, 16 hours, which that's almost half of a semester if we're thinking about a 3 credit hour class. Let me know if you have any questions. If you're ever out on a job and you have a rigging question, give me a call, send me a text. I don't plan on changing my phone number anytime soon.
Oh, wow. That guy's cool. Huh. Well, I think that is honestly about it for material. I don't foresee having much else to learn until I gotta read, so I think I'm gonna go ahead and wrap up the stream there, and I'll catch y'all later. Deuces. I'll probably stream here in a little bit.